Thank you. Okay, so let's go ahead and get started. My name is Paul Stey. I work at the Center for Computation and Visualization, CCV, and we're going to talk quickly about Rust today. So what is Rust? Some of you might have heard of the book, the Rust programming language. This is kind of the Bible for the programming language, and I kind of like this description sort of early on. It wasn't always so clear, but the Rust programming language is fundamentally about empowerment. I kind of like that a lot. I think it's a language that is very powerful and enables us to do powerful things. So Rust is traditionally described as a systems programming language. It's compiled, so we know the type of everything before we run it. It is strongly typed, so it's not so easy to kind of cast between types. It is very fast, and my claim is that it is fun. So in terms of its design, it's mostly functional-ish, but also has elements of imperativeness. It's not object-oriented in kind of the traditional sense or in the classical sense, but you can define structs and methods on those structs, and we'll see that in a little bit. So without further ado, here is some Rust code. So this is just a simple function to compute Fibonacci numbers. So a couple of things you'll notice right at the outset. We have type annotations, but only in the function signature. Rust has immutability by default. So if you want something to be mutable, you have to declare that thing as mutable when you initiate it. And the last thing to note is that Rust is very expression oriented. So we don't need a return statement. A function will just evaluate the last thing and then return that. You can have a return statement if you want to return early, or if you just like return statements. I should also mention, if anyone has questions, feel free to interrupt me, raise your virtual or physical hand. So Rust has been around now for, I guess, almost 20 years, which is crazy because I still think of it as a fairly new language. So it hit 1.0 in 2015. It's something interesting that it's updated every 6 weeks, and the current version is 1.82. Okay, so I kind of mentioned this. Rust was originally envisioned as a systems programming language. There's not a really super clear definition of what a systems programming language is, but usually it means something like have direct access to memory, very high performant, and used to build things like web browsers or operating systems or things that require a high degree of control and performance. So why use Rust? I kind of mentioned these two: performance, safety, tooling, and because it's just a fun language. Rust has been voted the most loved language in the Stack Overflow, I guess, survey that they run every year, the last 9 years in a row. It's also growing use in scientific community. Folks might be familiar with the Polars package, which is kind of analog to pandas in Python, but it's all Rust under the hood. In terms of its similarities and differences to other languages, it's probably the most similar to C++, kind of syntactically, and also maybe in spirit. This notion of zero cost abstractions is very prominent in both languages. They also both have manual memory management and no garbage collector. It's also inspired by sort of Haskell and the ML family of languages, in the sense that it has, first functions are first class citizens. We have higher order functions. We have immutable types. So all those kind of things that you get from, the ML languages. Differences from other languages. One big difference is that this concept of ownership. So every value in Rust has a variable that's called its owner. There can only be one owner at a time, and when an owner goes out of scope, the value is dropped, and we'll see what that looks like in just a second. So here is us creating a string called S1. We then assign the contents of S1 to S2, and we get an error when we call print line with S1. And as we'll see in a couple of these, the error messages in Rust are extremely thorough, and it basically tells us exactly what's going on. So it says error borrow of moved value S1. So S1 is a moved value. We'll learn what that means in a second. So the move occurs here because S1 has type string, which does not implement the copy trait. So we see that the value is moved here. And the compiler here tells us exactly what to do. So help consider cloning the value if performance cost is acceptable. So using the clone method. We do that, we in fact have no problem. So just to kind of go back. So the issue was that when we do this, we've seen this in lots of other programming languages. You assign one value from one variable to another. In Rust, this has the sort of I guess unusual or somewhat surprising effect that it actually moves the underlying data, and it leaves no data in S1. So it makes S2 the owner of that underlying hello string. So to kind of get around that, we can create a clone, which is essentially just a deep copy, as I think other languages would call it. So we don't want to go around cloning things all the time. That doesn't seem like it's an efficient thing. So Rust also has this concept of borrowing. Borrowing is basically passing things by reference. So by default, Rust's functions are pass by value or call by value. So if we want to pass a reference, we need to explicitly say, hey, this is a reference. And that's what we're doing here. So again, the ampersand symbol, like in some other languages you might have seen, it denotes that the thing is a reference. So S is not a string, it is a reference to a string. And we can see here that that seems to work the way we would expect it. Any questions about all that so far? Great. So in addition to having references, Rust also has mutable references. So suppose we want our function to take a reference to a string and then modify that string. So this is what we're attempting to do here, and we get an error. And again, the compiler gives us a very informative error message, and it even, again, gives us the solution. So it says, help, consider changing this to be a mutable reference. So we go ahead and do that. And again, the only change here we've made is we added the mute keyword. So it's not a reference to a string, it's a reference to a mutable string. And now our function should work the way we expect. Everyone okay with that? We can also have multiple references. So it's possible to have, as many a number of references to the same piece of data as we'd like. Which is nice, but it's also, it needs to be caveated with, you cannot have multiple references if one of the references is mutable. And the reason for that is sort of clear. So here's us trying to create two references to the same string. And the compiler is going to complain because immutable borrow occurs here, and then immutable borrow occurs here. So the compiler won't let us do that, kind of for the sort of obvious reason that if you have two references to the same piece of data and one reference can modify that data, you'll run into problems where the other reference doesn't really know what's going on, and can be subject to all types of undesirable side effects. Okay, so Rust's borrow checker, as it's called, prevents us from having dangling pointers. So a dangling pointer is a reference to a location in memory that may have been given to someone else. So here we create a function called dangle. It creates a string and then tries to return a reference to that string. The compiler is going to complain and not let us do this because the data is in S, right? And S goes out of scope as soon as this function call finishes. So we can't return a reference to a piece of data that's been dropped because there'll be nothing there. The compiler won't let us do that. So you can see here, kind of, it gives us a very verbose error message, and you kind of get the idea. This makes sense. Everyone okay with that? Great. Okay, so the sort of two critical rules of references. At any given time, you can have either one mutable reference or any number of immutable references. And then the second rule, kind of, all references must always be valid. We can also create our own types in Rust using struct and enum. This will look similar if you've seen in other languages. So we define a new type. We call that type user. This is done with the struct keyword. Then we have these four fields in the struct. And again, when we're declaring a new thing like a function or a struct, we need to pass type annotations to say what kinds of things are these. Can then go ahead and create an instance of that struct just using the name of the type, and then we fill in the fields. And then we can access the fields by using the kind of familiar dot notation. We can modify struct fields, but by default, they're immutable. So if we want to, let's say, increment a count value in our user struct, we're going to get an error. If we want to not get that error, we need to declare the the variable as mutable when we initiate. So that will work the way we would expect. You can also define methods on structs. So again, despite not being object-oriented in kind of the traditional sense, you can get similar-ish kind of behavior. There's no concept of inheritance or anything like that in Rust, but you can have methods that are defined on a type, which starts to feel a lot like, objects in the classical sense. So we define a struct called a rectangle. We can then implement behavior of the rectangle in this impl block. So say impl rectangle, and then define a method called area, which just computes the area. And then here, this is us creating an instance of a rectangle, and then we compute the area, and it kind of behaves the way we think it ought to. It's okay with everyone. This is kind of a different pattern than a lot of languages use, but it's fairly intuitive, I have found. All right, great. We can also create different kind of types called enums. These are sometimes called algebraic data types, and these let us do really interesting things. So an enum is basically it's a type that only has a certain number of values. These are enumerated values. We call these variants. So we create a type coin, and it can be a penny, nickel, dime, or quarter. Then we get to use the really cool match operator, I guess, in Rust, which lets us do things like similar to an if statement, except we match not just on a Boolean value, we match on a type of something, and in this case, a type of coin. Yeah, question.
Some other examples of matching would it be?
Yeah. Yeah, so the question was, what are some other examples of matching? And we'll see a couple other examples in just 1 second. Match is quite powerful, and it's very ubiquitous in Rust. So here we create an instance of a coin. It's a dime. We then pass it to our function, and the function kind of does what you would expect. It gives us back a 10. So a very brief aside on match. Like I said, it's sort of similar to an if else, but we can match on anything, not just a Boolean value, and that lets us do sort of interesting things. And one other feature is match forces us to be exhaustive in terms of the variance. So if we match on a type coin, we cannot omit, I guess, what do we omit here? The quarter. Yeah, we cannot define a match operation if we don't include every variant. So that's kind of a nice way to prevent errors. Here's kind of an example of us matching on something different. So this is a function that describes a number that we pass it. And then, if it's a 1, we print line 1. If it's any of these 2, 3, 5, 7, or 11, it prints this is a prime. And if it's, in the range 13 to 19 inclusive, then it prints a teen. And then we have this kind of the underscore character is kind of Rust catch-all character. This will handle everything. This is kind of like the default case. So when we pass that number, 11 is a prime, 117 is nothing special. You get the idea. But to your point, you can match, or to your earlier question, you can match on all sorts of things. So enumerated types, then basic types like integers, floats, anything. So it doesn't need to be numerically based. No, you can, I mean, and actually you can, like we did, you can define your own type using enum or struct and then dispatch on that. Yep. Okay, so I'm going to talk briefly about two sort of special and privileged enums in Rust, which is the option and the result type. So the option type is kind of Rust's answer to null. There are no nulls in Rust. There are instead there are options. So option gives us a way to represent missingness. It lets us kind of return something when there's really nothing there. It basically makes us explicitly handle all instances in which something might be missing when it gets back to us. So the option type is in the standard library, and it looks basically like this. So an enum with 2 variants, some which carries some data of type T, and none, which is just none. So here's us creating an instance of an option type. We use the sum variant, and we can then take the type of, we see, the first one is an option I32. Second one is an option reference to string. You get the idea. So if we want to work with options, we need to be a little bit more verbose. Again, this is the idea of like explicitness is better than implicitness. So if we have X and Y and we're trying to take the sum, if we try and do that kind of without unwrapping the option, we're going to get an error. And it, again, the compiler is extremely thorough, so we cannot add option I8 to I8. So if we want to do that, we need to unwrap, which we do with the unwrap method, and that just gets the data sort of underneath it. Some folks will say that we really shouldn't be calling unwrap. We should be doing something that handles things more intelligently, because if we call unwrap on a on something that's not there, then our program will crash, like the thread will panic and will crash. And that's what this is. So yeah, so folks will argue, well, we should really be using match, or we should be handling this in a more sort of robust or recoverable way. And I'm pretty sympathetic to that view myself, actually. And we can, of course, match on the option type, as I mentioned. So this might be a way to sort of handle the missingness more elegantly. So here is a function that takes some value in option I32 and returns an option I32 with the value inside it being incremented. So that kind of, behaves sort of the way we would expect. Unwrap or is a nice maybe alternative to unwrap. Unwrap or sort of does what you would expect. So it unwraps the option, and if there's nothing there, it returns this default value. So in this case, we're defining the default value to be 0. So if it unwraps X and X is none, then it's just going to say, okay, X is actually 0. Then it's going to increment it and return it. Any questions around that, or anything related to the option type? At first, it felt really heavyweight to me, and it felt like kind of laborious to have to always check whether it's a thing or not a thing. But I found kind of get over that pretty quickly. Okay, so the results type, Rust does not have exceptions. Instead, we have what we distinguish between recoverable and unrecoverable errors. So the result type is what you use when you have an error from which you can recover. And the panic macro is what's used when you cannot recover. So something from which you cannot recover is like you have used up all the memory and now your program doesn't have any memory. That's not a recoverable error. So your program will just crash. And so here's an example of something that actually should be a recoverable error. So we match on F, a file handle. And if F is a file, then we kind of unpack and return that F exists. And if not, we panic. Again, here we should actually be doing something more intelligent. We should not panic if the file's not there. We should prompt and say, hey, do you want to give us a different file name or something? Okay, so now we've looked at enough Rust to have more than a toy example. I should also mention the I'm doing all this in a Jupyter notebook, which is like super not a Rusty thing to do. I'm surprised. Oh no, I shouldn't be surprised. There's a Rust kernel, but I do not recommend using Jupyter notebooks for writing Rust or other things actually. But it's very convenient because it allows me to take these this notebook, and each cell is a slide with this plugin, which I really like. But with that said, I usually don't use notebooks, and for something more than a toy example, I think it's worth just actually looking at the code in an actual editor. So here is a small program that we're going to run written in Rust. We're going to run it and then sort of look at it. This is a guessing game, so we need to guess the number between 1 and 100. 50 is too big. 25. Great. Okay, so that's a pretty simple little guessing game, and let's look at the actual Rust code that did all that. Can folks see that okay? It's kind of dark. So, okay, so we print a little like intro message, and then we say, hey, generate a secret number. So we use just our random number generator. Then we enter this loop. So not all languages have a just plain loop construct. This is essentially the equivalent of while true, but this is just going to loop infinitely until it breaks. So we initialize some input variable, we call that guess, and then we read from standard in and put that value in guess. And note, again, if you want something to be mutable in Rust, you have to say that when you declare it. Otherwise, immutability is always assumed by default. Okay, so we read line from standard in. Expect is the method used that is a method similar to unwrap in the sense that if we read from standard in and there's nothing there, this will crash or throw an error. And that is essentially what unwrap does, except for options rather than results. Then we are using a little bit of matching magic to get the actual number. And if it's not a number, it just goes back to the top of the loop. So the continue keyword is just going to throw us back to the top of the loop. If it is a number, so if we are able to match that and cast it as a U32, then we're going to go on and compare it. So we use the CMP method to compare the guess to the actual number, and then we print if it's too big, then we print too big. You get the idea. Folks okay with this? This is a pretty small, simple program, but fairly illustrative in terms of some of the constructs that are in Rust. Great. Okay, so some common collection types that you have seen in other language: a vector, a string, and a hash map. So there are a few different array-like data structures in Rust. The vector type, or vec of t, is what you use when you want to store more than one value in a single data structure. This puts all the values kind of next to each other in memory. But note that, like in some other languages, we can only store one type of thing. So this is not like a Python list type object where you can have heterogeneous data. This is like a one type of thing. So vec of t means you have type t. And here's us creating a vector. Let's see. So note that we get an error if we don't declare v1 as mutable. Again, immutability is assumed by default. I don't actually know that we need this type annotation here. Yeah. It's more common to initialize vectors with the vec macro, and that's done just using vec exclamation mark and then pass it the list of elements that you want to make into a vector. You can then push elements into that vector just like we did before. Accessing values can be done either using the sort of familiar square bracket notation or this get method. I think many people say get is preferred, and that's strictly because get will not panic if we try and access something out of bounds, whereas a square bracket notation, it will crash. So some extra sort of safety guarantees if we use the get method. Everyone okay with this? Great. Okay, so this is an interesting nuance. So accessing elements of vec is sort of interesting in that we can't do that and modify. So we can't take a reference to an element of a vector and also modify that vector. And the reason is it's sort of what we talked about before, which is that you can't have an immutable borrow. So this, let first be a reference to v0. This is an immutable borrow. And it's not, we don't think of it as a borrow, but this call to the push method is actually a mutable borrow. So we can't do both of those things at once. And again, the reason is that calling a method like push that is modifying the underlying data, that could break whatever we're doing with the immutable reference. If the modification to v is such that the operating system needs to move the data to somewhere else in memory, that would break the immutable reference that we have here from let first equal v of 0. Does that make sense? I didn't explain that super clearly. Is that okay? Great. So we can iterate over values, just kind of how you would in other languages. This is not so shocking. If we want to iterate and modify the values, we need to use the dereference operator, which you've maybe seen in some other languages, C or C++ or Go. The string type is sort of interesting for a couple of reasons. So the core language, Rust, has a string type that's a string slice. This is sometimes just called stir. It's usually seen in its borrowed form, so ampersand stir. And it's just a reference to some UTF-8 encoded data stored somewhere. The string type, the string, capital S string, is part of the standard library, not the core language. And it is mutable, it is growable, but it's also like just a regular UTF-8 encoded string data. So if we create a new string, remember we need to say it's mute, and we can push stir into it, and that kind of gives us what we would expect. Okay, so moves in Rust, I think I'm gonna skip yeah, I'm gonna skip that. Well, let's not ignore it completely. So moves are sort of interesting. This is what we saw at the beginning. So this is not so obvious that this is a move. So this is taking the data in S and putting it in S1. So then when we try and print the contents of S, we get an error. The value has been moved. If you'll recall from the beginning, this is what we solved by doing clone, and that seemed to work fine. But again, suppose we don't want to use clone all the time, and then that gets a little bit more difficult. But what I want to point out here, though, is this sort of second case, actually. So this second case, so let n equal 137, and then n1 gets n. This is going to work. And the reason that it works is really not at all obvious. But the reason is that there's a difference between capital S string and an I32, which is that an I32 implements the copy trait, and we'll talk about traits in just a little bit. But basically, the copy trait is it is a behavior such that if you use the assignment operator on a type that implements copy, the type is actually going to give you a copy, not move the data. So in the first case, we're moving the data that's in S. In the second case, we're making a copy of the data that's in N. Does that make sense? Any questions on that? That's kind of a subtlety. Great. Okay, so this is similarly true for vec. So vec does not implement copy. So when we say v1 gets the contents of v, what we've just done is moved the data from v into v1. And again, we can fix this using clone, but we don't really want to do that. I'm going to skip all this. Okay, so I said this already. We can use clone. It kind of gets around this. Clone's making a deep copy. Okay, the hash map. A hash map, or sometimes called dictionary in other languages, is basically a sort of associative data structure where you have some key and have some value. These are not too surprising in how they're implemented in Rust, and they're very useful. The functional language features of Rust are pretty interesting. So Rust has closures or anonymous functions, sometimes called lambdas. I feel actually sort of silly. It's only recently that I realized that in both JavaScript and in R, every function is a closure. I didn't really realize that, but that's sort of interesting. And kind of we'll see how that behavior manifests. So if you haven't used closures much before, closures are sort of interesting in that they're very similar to functions, but they have access to the data in the environment in which they were defined. So here we're defining a closure using this kind of pipe notation. So pipe, encloses the arguments to the closure, and then we have the curly braces that denotes the kind of body of the closure. So here we're defining a closure equal to X. And what that closure is doing is we give it some input variable Z, and it's going to return a Boolean value indicating whether or not that Z is equal to X. But what's interesting is we don't pass X to this function, this closure. It's just able to access it by virtue of being defined in the same environment where X is defined. So X is defined in this main function body, and equal to X has access to it because they're both defined in that same scope. I hope that makes sense. But again, it's something that is, if you're coming from JavaScript, you use closures all the time without even thinking about it. And I guess similarly in R, although it doesn't seem like R programmers do so as much as JavaScript. Does this make sense though? Everyone okay with this?
One disadvantage then is that of using closure, functions ask closure, because that it could be confusing later when you see something defined within a function. Not defined within a function, but it's used in there. And you have hundreds of lines of code above it, and then you have no idea where that object that's been used within the closure is from.
Yep.
I like using closure other than using them as closure.
Yep. So the question, or I guess more comment in the room was, we kind of have to be a little bit careful with how we use closures because there's because what they do is a little bit magical compared to other functions. There's the potential to kind of like lose track of what the closure has access to or does not have access to. I think that's fair. I think they need to be used sort of carefully. Okay, so if we attempt to do the same thing but with a function, so here, you know, the closure was just defined using a kind of pipe notation, and here we define a function using the fn keyword. If we attempt this, we're going to get an error. Okay, iterators. Iterators are, you know, fairly common structure that you've probably seen in other languages, but it lets us write pretty terse, readable code. So the real strength of iterators is kind of the ability to chain them together. So here we can take some vector, we can convert it to an iterator using the iter method, and then we can call something like for each to iterate over every value. And it kind of behaves the way the for loop above did. Okay, so iterators have many different methods defined on them, and there are two kinds of methods: the sort of consuming adapters and iterator adapters. So consuming adapters, you know, consume the value they're iterating over and return a new value. Iterator adapters return a new iterator, and we'll see some examples here. So this is an example of a consuming adapter. We have some vector, it has some numbers, we convert that to an iterator, and then we take the sum. So the total variable is just, you know, that's us consuming the iterator. And then an iterator adapter is something like this. So we have, again, a vector of numbers, and we convert it to an iterator, and then we use the map method so map is a sort of higher order function that takes closure here. The closure is x times x. That's basically just us squaring the value. But this is an example of us using an iterator adapter, which is to say an iterator that returns another iterator. So here we're returning iter with these values.
Question.
Yep, question.
Lazy. And
Yeah, that's a great question. You can actually see the result here. The answer is yes. So we're returning iter with the original values. We haven't done anything. We haven't squared those values, which is what we're doing when we like consume it. So if we wanted to like get something back, or oops, then we would have to call a consuming adapter, which we do right here. So in this example, so we're still calling iter, and then we're calling map, and again, we're just squaring the integers, and we use the collect method. So collect is a consuming adapter, and that actually executes the map function, or the map method on the iterator.
so once they are consumed, the members of the iterator, you cannot go back and try to reconsume them again.
I think the answer to that is yes, but let's confirm that. So I think so the question for Zoom was, once you consume the iterator, you can't go back. And I think the answer to that is yes. So let's um
You know, in languages like Python, you can't do that. If you find it, you consume it, but if you refer back to it, it's empty. You can no longer consume the memory.
yeah, I think I think the answer is yes. I think when you consume it, they're gone. I'm pretty sure of that. Okay, so we said this already. So iterators are lazy, which is to say the computation isn't executed until you need the result. So so here, if we remove this collect, it's never going to call print line. Oh, yeah. Um, yeah. Yeah, so the kind of key idea here is what we said before, like none of this gets executed unless we call a consuming adapter, which is what the collect was doing. Okay, generic types, traits, and lifetimes. These are three sort of meaty topics that could have their own talk entirely. So generics, you might have seen in other languages. If you use C++, because this is kind of like templates, I think there are generics in Go, TypeScript has generics. They basically allow us to avoid the kind of duplication of code. So say we have some function that computes the largest integer in some list of integers. So that would look something like this, or could look something like this. Basically, we take the initial value and then we iterate over each element. And then if the element which we're iterating over is larger than the current largest, we promote that current element to the new largest, and then we return that. And we could do something similar for characters. So if we say the same thing, but now we're passing it not an array of I32, but instead an array of characters, we do basically literally the same thing. So the only thing different between these two functions is literally the type signature, nothing else changes. So wouldn't it be nice if we had some way to kind of abstract that, like the sort of business logic out, and have something that's generic? So what might that look like? Well, it could look something like this, where we parameterize the function largest over type T, and then we pass it some reference to array of type T. Again, the entire business logic here, body of the function, is all the same as it was in the two prior functions. The only thing we've changed is we now have this kind of angle bracket type T annotation. So this version is actually very, very close to working. This doesn't quite work. I kind of drew this up as pseudocode, but we'll see in just a little bit how to make it work, basically. So it's funny, the error message here actually tells us something very close to what will be the eventual solution. So in addition to having generics over our functions, we can also have generics over our types. So here we define a struct, a type called point. It's generic over type T, and it has two members, X and Y, which are both of type T. We can then create instances of that struct, and we can have those be of type int or of type float. And you kind of get the idea. So this is how generics work for types that we create ourselves. Everyone good with this? Any questions here? Great. Oops. Oh yeah, and if we try to pass a float and an int, the compiler is going to complain. says both X and Y must be of type T. If we wanted them to be of different types, we would have to say these can both be okay, and then that would work.
Is that sort of like a union thing? You do that?
Okay, so traits in Rust are sort of interesting. If you've used Java or JVM-like language, you'll know these as it's very similar to interfaces in those language. But traits are basically a way of defining shared behavior. So that is essentially saying a set of methods that this type must implement. So for a trait to implement, or for a type to implement a certain trait, it's kind of like a contract. It must implement these methods. So what does that look like? And we'll go back to actual terminal and so here is us defining a trait. That trait is called summary. So summary is it's a trait that we're going to implement for our two types, news article and tweet. So we just need to implement a method for each of these types that that implements these summarized traits. So so summary is a trait with only a single method. So for us to kind of like, you know, fulfill that contract for news article and for tweet, we just need to implement that one method. And again, summarize just takes self by reference and returns a string. So that's all we need to do is implement the method for both news article, which we do here, and for tweet, which we do here. And you'll note that all we're doing is we're defining the method, and we kind of just give back a string. In the case of the news article, we give back the headline, the author, and the location. In the case of the tweet, to summarize means to give back the username as well as the body of the content. So that's kind of the idea. Again, it's sort of like interfaces in Java, but not identical. It's basically you know, a trait is a set of behaviors, methods basically. So for our type to implement the trait, we just need an implementation of the method that is part of that trait. Does this make sense? Traits are very useful in languages that don't have like classical inheritance, like object-oriented. Again, it's basically a way of defining shared behavior.
Do you like the equivalent of a class in Python?
So the question was, it's the equivalent of a class in Python. Yes-ish. So yes-ish. So in this example, it's more like it would be like multiple classes, one that inherits from the other, or two classes that inherit from the same base class, if that makes sense. So if this were Python, the struct would be a class. So we would have two different classes. So you get what I mean? This kind of like, exactly. That's exactly right. Yeah. Yeah. So so the question was, is this like class in Python? And the answer is yes, there's an element of that, but it's more like two classes in Python that have the same base class, or that both inherit from the same base class. Okay, so traits and generics have kind of an important relationship, which is that the generics often need to implement traits, and we'll call that trait bounds, and we'll see what that means in just a second. So if you'll recall, this is our previous kind of pseudocode example that almost works. So this is meant to be a function that's generic over T, and it's going to iterate over the elements of this input list and then return the largest for some definition of larger. And we see this error message is actually quite helpful. So the operation greater than cannot be applied to type T. T could be anything. So, you know, can't have greater than applied to anything. So it says help consider restricting type parameter such that it implements standard comp partial word. And in fact, that's exactly what we're going to do. So we actually need to implement partial or and copy. So this is the trait bounds notation that I mentioned above. So we're defining our function, and then in the type signature, we say largest is generic over T, and it implements partial or and copy. And then everything else is kind of the same as the pseudocode. We take some input list. It is a reference to a slice of type T, and we return a variable that is of type T. So now this should work the way we expect, which is to say it should be a single function that works kind of generically, and seems like that does in fact work. Any questions on this? The noisy type annotation in the function signature is definitely something that I think turns people off a little bit at first. It does start to feel a little bit like this is a very busy function signature, but I've found that it actually gets pretty familiar. I think there's a raised hand.
Yeah, I had a question, Paul. So it looks like you can define those, partial ORed, for example, on something at any time. So the order of that would make it work or not work at that point. Is that, I mean, because these things are kind of in your source code, the time at which you might have that be valid would depend on whether it's already been defined or not. Is that true?
Sorry, David, could you repeat the partial ORed and the copy you're referring
Well,
to?
sorry, you said that you need to have, like, in this case, partial ORed and copy defined on the type for it to actually work, right? For largest, is that, or, oh, I was wondering the order in which you actually defined the new type and had its partial or copy trait, is that trait, right? Or
Yep.
defined at that point. Like in the source code, does it matter when the actual happens?
Does it matter when it actually happens? So David, you're asking if it matters when, so I should clarify, partial ORed and copy are both traits that are defined in the, I think in the standard library or in the Rust core language.
But a new type could have them defined, right? Or not?
Correct. Yes, that's exactly right.
So if that new type, but the time at which that new type was described or defined could come after this function, but that doesn't matter?
That is correct. Yes, that is correct. Well, yeah, that is correct. I mean, so the compiler will handle that at compile time, but yes, it is the case that you could write a function that operates on some type T, and let's say we implement T ourselves, as long as that type, we also implement partial ORed and copy for that type, that will be fine, and order should not matter. I'm nearly certain of that, but I think the compiler would handle that.
Okay, cool.
Yeah,
Thank you.
good question. Okay. All right, lifetimes. Lifetimes are super interesting feature in Rust. So every reference has a lifetime. A lifetime is the scope for which a reference is valid, and we'll see a little graphic of that in just a second. So we sometimes need to specify a generic lifetime parameter explicitly in our code, and that's kind of a little weird annotation that probably will look a little funny at first. Lifetimes basically prevent dangling references. This eliminates kind of an entire class of errors. Okay, so here is us, and recall that curly braces introduce scopes in Rust. So here's us with an outer scope and an inner scope. In the outer scope, we instantiate a variable called R. We're going to try and make that a reference to X, but that happens in the inner scope. So here we say X gets 5, and then we try and take a reference to X here. And when we try and print the contents of that in the outer scope again, we're going to get an error message. And again, the reason is like nicely articulated in the error message. So it says error, X does not live long enough. So the binding X is declared here, that's in the inner scope, and then borrowed here, again in the inner scope, and then it's dropped at the end of that inner scope here. So then we try and use a borrowed value, which does not work. Whoops. Okay, so this is kind of the sort of graphical representation of the lifetime. So R has lifetime tick A, and X has lifetime tick B. And when we try and access the value of R, it's gonna throw an error because that value no longer exists. It was dropped at the here, the end of the inner scope. So in some cases, we need to include generic lifetime annotations as part of our function definitions. So if we have some function here called longest that returns whichever string is longest. We try and define that and we get an error. Now it's sort of curious because it seems like this should work. This is a function that takes two stir slices and then returns whichever one is longest. That doesn't seem like it's a complicated thing. But again, the compiler is telling us we need a named lifetime parameter. And oops. The way that we do lifetime annotations is a little bit funky in Rust, or at least it wasn't super intuitive at first, but this is kind of the idea. So here, these are kind of the most conventionally used lifetime parameters: tick A, tick B, tick C, etc. They're usually single characters, and they're always kind of prefaced with that single quote. So here, ampersand I32 is a reference. Ampersand tick A I32 is a reference with an explicit lifetime, and then ampersand tick A mute I32 is a mutable reference with an explicit lifetime. So it gets a little messy, I'll be honest, but you get used to it. So here is our function. We're fixing it with the tick A type annotation. So we say longest has the generic lifetime parameter tick A. X has generic lifetime parameter tick A, and so does Y. And then the result also has a generic lifetime parameter tick A, and this should work. Any questions about that? It's a little weird, I know. It's a little weird.
Paul, how should we read the A there? Is it just like a placeholder?
Yeah, that's a good question. It's not so much a place. Yeah, that's a good question. It's kind of a placeholder in the same way that like the generic lifetime parameter T is a placeholder. So it's actually, so lifetimes are actually a compile time construct. So if your code compiles and then you try and introspect the code as it's running, there's no concept of lifetimes. You can't like introspect the lifetime of X or Y as the code is running. The lifetimes rather are they're a compile time check basically. And what they're checking is that they want to make sure that the returned value. So these lifetime annotations appear when we have functions or structs that give us back a reference. And here we're returning a reference, we're returning either X or Y, depending on which is the longest. And basically what our lifetime annotations are saying is that the lifetime of the thing that we return is the shortest lifetime of the two things that we're comparing. So if either of those things are out of scope before the time that we refer back to the thing that we're returning from this function, that code won't compile. So it's basically a compile time check to make sure that we don't return a reference to data that is no longer there. That's
So
really what it is.
is the key here that they're all A? I mean, if you put A and B, it wouldn't make any sense because you can't say what you're going to return at that point.
That's exactly right. So and actually, if we do this, I don't even think that'll compile. Yeah, I mean, that's wrong. Yeah, lifetime may not live long enough. Function was supposed to return data with lifetime tick A, but is returning data with lifetime tick B.
Somehow the return would have to indicate it could be A or B, but it doesn't. It says
Exactly.
it's ampersand.
Yeah, that's exactly right. Yeah, so they're basically a compile time construct that prevents us from returning a reference to data that is no longer there. Okay, so lifetime elision is kind of this, it's this interesting sort of phenomenon or set of rules really that says that we don't generally have to do a lot of lifetime annotations. There's a lot of cases in which the Rust compiler will just handle that. So one example might be if you have a function that takes in a reference and returns a reference, those two are going to be tied. We won't need to do lifetime annotation because there's only one reference lifetime that's in question, the reference lifetime of the input variable. That's essentially what this is doing here. We don't need a lifetime annotation, even though we're taking in a reference and returning a reference, because those two lifetimes are going to be the same. Does that make sense? This is kind of one of the rules where we can do lifetime elision, which is to say we don't have to specify the, we don't have to use generic lifetime parameters to kind of describe the relationship. I guess that's it. Thank you all.
Thank you, super helpful.
Thank you.
I feel like more and more people are kind of transferring their kind of like methods into Rust. Is that like why? I guess it's kind of a question.
So the question is, why are people kind of,
Why are they like migrating all the things that they've already written?
yeah, so the question is, why are people migrating all the things they've already written to Rust? I guess I would say there's probably a few good reasons and many bad reasons. I think the language has gotten very popular because it's a powerful language that feels pretty fun to use. I think there's also a novelty to it. People like using the new things. I also think that it's just it's a language that gives you a very high degree of power and control while also sort of preventing you from doing things that like in C or C++ would be like, risky or dangerous, or you'd have to be very careful about. So I think from my perspective, if you're like, if you're writing like some small, like, CLI, some command line app, and you care about performance a great deal, I think it would be a very reasonable choice. But you also see examples like the polars package in Python, where that is, I would claim that, 10 years ago, that would have been written in C++ and then, exposed in Python. That's basically what pandas is. So I don't know. I think there's a bit of a bandwagon effect and people like to do the new thing. I think that's a piece of it. But I think there's like, I think fundamentally it's a very powerful language that is a pleasure to use. The tooling, I didn't talk about it, but like the build tool and package manager called Cargo that ships with Rust is like, that is enough of a reason. Like in my time with any programming language, I've not seen a nicer build tool package manager. Like Cargo is the absolute, like, I'd say they set the new standard. It is unbelievably pleasant to use. I think that's from my perspective, there's basically two things that sort of determine how a language feels. That is the type system. So what kinds of things can you declare, and the tooling around it. So the type system is so fundamental to a language, but also fundamental is like, what are the tools that you use to build your programs or to build your libraries, et cetera. And I feel like Rust does very, very well in both those areas. Sure. Any other questions? Yeah, and sometimes the speed is shocking coming from Python. Yeah, that's definitely true. You can often get very, very good performance. Okay, I think that's it. Thank you all.